Okay, hello and welcome to this third ever event of PHO2, the joint new research seminar of the Center for the Philosophical Studies of History and the Center for the Philosophy of Historiography. PHO2 stands for Ostrava Olu or Olu Ostrava Research Seminar in the Philosophy of History. My name is Georg Gangl and I will be today's moderator. More importantly, today's speaker is Jamee Elder with the topic Astronomy, Cosmology, and the Distant Past. Jamee is currently assistant professor in philosophy at Tufts University in the US, and she's also an affiliate member of the Black Hole Initiative at Harvard University. Her main research interests lie in the philosophy of physics and the philosophy of astrophysics, and here especially in the methodology and epistemology of large astrophysical experiments and the uses of models and simulations in them. Now, of Jamee's many publications in her main research area, I only want to mention two forthcoming papers here, but I encourage all of you to check out her publications by yourself. One of them is How Theory-Laden Observations of Black Holes that Jamee co-authored together with Juliusz Dobrzewski, and which will come out in Philosophy of Science, the Journal of Philosophy of Science. And the other is Astronomy, Cosmology, and a Distant Past, which will appear in the forthcoming handbook, Bloomsbury Handbook of the Historical Sciences and Big History. This handbook should come out in September of this year, and it was edited by Aviesa Tucker and David Czernin from the Center for the Philosophy of Historiography, and I also happen to have a chapter in there. After today, we will still have two more events in our spring cycle of PHO2. First, on May 29, there will be Arthur Alfaiz Assis, who I also see here already today, of the University of Brasilia, speaking about COSELEC and the concept of history. And then finally, on June 17, we will have two talks. It's a bit of a little workshop on contingency in history. And there we will be speaking Gregory Redick from Leeds University on with the topic From Cleopatra's Nose to Darwin's Nose, J.B. Bury on history, science, and contingency. And we will also have Robert Northcott from Birkbeck College in London speaking on contingency and history, but the topic is still to be determined. Both of these, or three of these talks, but both of these events will take place on Zoom, and the event on contingency and history will be hybrid. It will also take in person in Ostrava, so you can join in either locale, online or in Ostrava. More information will be published on our homepage and our social media accounts closer to the events. Now, if you want to stay updated about our activities of both centers, I suggest you follow our social media accounts. We have the Center for Philosophical Studies of History has X, Facebook, and Blue Sky, and the uh, Center for the Philosophy of Historiography has Blue Sky so far, and soon also Facebook, hopefully. And there are quite a few more events in the planning, so it's worthwhile to check it out regularly. Now, before I give the word to Jamee, a few technicalities. Please mute yourself during the talk to avoid any unnecessary disturbance. And after the talk, there will be a discussion session that I will moderate. I think Jamee will speak around 45 minutes. In the discussion session, if you have a question or comment, please first indicate so in the chat. I will make a speakers list. When it's your turn, you can either speak up without your camera on, or you can write your question in the chat, and then I will read it out loud. And we will prioritize people who have not spoken yet, so they will move up on the speakers list. So thank you very much. That was it from me. Thank you very much, especially Jamee, for accepting the invitation. The floor is yours. Please.
Great. I will share my slides. Thumb up if you can see it, I guess. Great. Okay, so I will go ahead and get started. Thank you for the wonderful introduction, and thank you for plugging the historical sciences volume that's coming out. Saved me doing so. Okay, let's click there, and we can proceed. So, today I'm going to be talking about astrophysics and cosmology as historical sciences. I want to start out by, sort of suggesting that there's at least one fairly obvious sense in which these two sciences are historical sciences, which is that they are dealing with objects and phenomena that are in the past and in many cases in the very distant past. Due to the finite speed of light, any signals that we're receiving on Earth left the objects of study a very long time ago. And so really they're signals from the very distant past. And so we can sort of think about observing the universe and kind of analogous to, looking in strata, and that as we look sort of further and further away, what we're really doing is looking further and further back in time, similar to how if you sort of dig further and further into layers in rock, you're sort of metaphorically speaking, digging further back in time. So there's this kind of, at least kind of shallow sense in which astrophysics and cosmology qualify as historical sciences. But today I want to ask whether there's something more to say here. So do astrophysics and cosmology have similar epistemologies to other historical sciences? And I want to answer that, at least to a large extent, yes. And second, what can we learn from this grouping? And so I'll bring that out in part through some case studies. I also want to point out that astrophysics and cosmology have faced, I think, some kind of similar criticisms um, from, uh, from in part philosophers, but they're sort of analogous criticisms to what you sometimes see sort of launched at other historical sciences. So, most famously in the context of astrophysics, Ian Hacking has this kind of this quote where he says, you know, the technology of astronomy and astrophysics has changed radically since ancient times, but its method remains exactly the same. Observe the heavenly bodies, construct models of the macrocosmos, try to bring observations and models into line. In contrast, the methods of the natural sciences have undergone a profound transformation, chiefly in the 17th century. Or one might say, the natural sciences came into being then and thereafter, while astronomy is not a natural science at all. And he goes on to sort of draw some fairly bleak conclusions about our abilities to sort of gain knowledge about astrophysical targets, um, and sort of ties this into a kind of broad anti-realism about astrophysics. Now, this has motivated a wide range of responses. In fact, I think much of the interest in philosophy of astrophysics kind of stems from this critique. And in many cases, philosophers have drawn some comparisons to astrophysics, between astrophysics and other historical sciences in the process of thinking through its methodology and kind of defending it from this kind of thoroughgoing attack. Okay, so for the rest of today, I'm going to start by sort of just talking fairly broadly about the sense in which astronomy and cosmology qualify as historical sciences, with a kind of emphasis on drawing some parallels between the methods that are used in these sciences and other historical sciences. And I use methods kind of fairly broadly here, thinking about sort of strategies of inference that are being employed. Um, I'll then move on to talking about two particular case studies. So one of these involves what's called the Hubble tension, which is to do with measuring the expansion of the universe. And the second involves black hole formation channels. So trying to understand how the black holes that we observe in the kind of relatively nearby, and therefore kind of relatively nearby temporally as well, universe, understanding how those black holes actually formed over the history of the universe. And then I'll end with some sort of brief philosophical reflections that kind of draw these things together. Right, so starting off with some broad comments about astronomy, cosmology, and historical methods. So I'm using astronomy and astrophysics fairly interchangeably here. One might draw distinctions, but in my experience, astronomers tend to interchangeably refer to themselves as astronomers and astrophysics. But what are astrophysics and cosmology? Um, Cosmology is a science that deals with the entire uh, history of the universe. So it's really studying a single object, and for that reason has sort of been described as an historical science par excellence. And I think the Stanford Encyclopedia of Philosophy article talking about cosmology. Um, in contrast, astrophysics tends to deal with the kind of more specific phenomena that occur within the universe. And um, nonetheless, these two sciences are going to be very intertwined. So while cosmology deals with kind of the whole history of the universe from the Big Bang through to the sort of formation of large scale structure, by which I mean things like uh, galaxy clusters, the kinds of things that you're looking at if you're looking at a really large scale. Um, Astrophysics is dealing with usually the smaller, more specific phenomena. Um, but the observations that these fields are using, the kinds of data that are being used, are going to be very much overlapping. And there's going to be a lot of feedback between the kinds of processes that are of interest to the two. So I'm going to talk a little interchangeably about these two sciences throughout the talk, although, in some cases, more particularly one than the other. Okay, so astronomy and cosmology, as we sort of already saw with this hacking criticism, um, are not sciences where you can easily go and intervene on the objects that you're studying. It's sort of unclear what it would even mean to go and intervene on the kind of universe as a whole. Um, but even in astrophysics, most of the entities that are being studied are very far away, um, maybe also on very large scales, often gravity dominated. And we just don't have easy means of going and intervening or performing kind of ordinary experiments on the objects of study. And so, much like in other historical sciences, we can think of astrophysics and cosmology as trace-based in the sense that we're really learning about these distant objects through whatever observations are possible here on Earth. So, just to be a little concrete here, I'm taking this formulation largely from Curie. Uh, we can think of a trace as a downstream consequence of some past entity, past event or entity, such that we can learn about that entity by studying the trace. Um, so to kind of bring out the kind of parallel here, we might think of something like a fossil as kind of a quintessential trace when we're studying, say, dinosaurs. In astrophysics, the traces might look a little different. Typically, we're going to be looking at something like observational data, and in this case, this graph on the left, um, this is results from the LIGO collaboration. These are the first observations of gravitational waves. And so the specific morphology of the signal is encoding information about the event that produced it. And in this case, it's thought to be a binary black hole merger. So very far away, a long time ago, two black holes merged. In doing so, they released a lot of energy, which was propagated through space in gravitational waves. And then, you know, a very long downstream consequence of this is that the LIGO collaboration was able to measure these gravitational waves on Earth. And so we can think of the gravitational waves as a trace of the binary black hole merger. So again, drawing on some of the way Curie sets this up, we can think of traces as evidence about the past and in virtue of some kind of mid-range theory and dependency relations between the trace and the entity. So in the gravitational wave case, there are sort of well worked out relationships between the properties of the black holes and the properties of the gravitational waves that we observe. There's this we have a good theory that tells us how these two depend on the other. Now, a kind of um, classic case of a trace in especially cosmology is the cosmic microwave background, which is sometimes even referred to as relic radiation. So what this radiation is it's very cold radiation that originates in the very early universe and what's sometimes called the time of last scattering. Basically, the universe used to be hot plasma that was opaque to light. But at some point, it underwent a kind of phase transition where light was suddenly able to propagate um, through the universe. And so this radiation originates at that time, and we can still observe it today. And we observe it no matter where in the sky we look, and it looks basically the same in every direction, which is to say it's isotropic. However, uh, there are these kind of slight um, uh, anisotropies. That is to say, there's these slight differences in different directions. They're very tiny. It's a very fine-grained kind of um, difference. But these differences are thought to be result from overdensities and underdensities in the early universe that eventually, through the forces of gravity, result in all of the structure that we currently observe. So things start off pretty flat. We have just kind of matter distributed evenly throughout the universe. Areas of overdensity through gravity eventually kind of pull more and more matter into them, and slight underdensities eventually get completely empty. And over the course of the entire history of the universe, um, this is kind of thought to be responsible for the pattern of galaxies that we see in the sky. So from this, we have this really fairly pristine trace of the way that the universe was at a past time. And from that, we can learn a lot through simulations that kind of match them up about the relationship between that and the structure that we actually observe in the sort of current universe. So I've talked now about traces, um, as sciences that don't tend to deal in kind of ordinary experiments. Um, Much has been made about the kind of methods that historical sciences employ instead of ordinary experiments. That is to say, trace-based methods. So using traces, what can we infer about the universe? So people have emphasized, for example, the what's sometimes called the Sherlock Holmes method, or the unification of traces by a common cause. Um, Others have emphasized the role of consilience, which you might also understand as robustness arguments. Um, Essentially, all of both of these methods involve using a variety of traces to kind of piece together information about the past. I'm not going to talk too much about these in this talk, but I'll just flag that I do talk about these a little bit in a little bit more detail, specifically in the context of gravitational wave astrophysics, in a paper that came out in last year in Studies in History and Philosophy of Science. Um, I'll just go through this quickly. I think for this audience, it's probably all a little bit old hat, but that's just good to get us all on the same page. So, in thinking about this first method, um, Cleland especially talks about the unification of diverse traces by positing a common cause, and a kind of example that she uses is um, this mass extinction event purportedly caused by an asteroid impact. Obviously, the science is complicated here, but this, the standard story goes, we have this fossil record showing mass extinction. Around the same time, there's these elevated iridium levels, this observation of shocked quartz, and finally the observation of this crater. All of these sort of seem to call for explanation, and if we posit a common cause, an asteroid impact, we can explain all of these diverse traces. And so this kind of method involves inferring a common cause based on the diverse traces that have been observed. Important for Cleveland especially is the methodology of searching for smoking guns. So this is, in some sense, a piece of evidence that really clinches the case. There's maybe interpretational issues about exactly what that entails, but in this kind of classic story, the shock quartz kind of play this role because it's the kind of piece of evidence that really decides between alternative hypotheses that were available until that point. And so the idea is that historical sciences are often guided by the search for smoking guns, in the sense that they're often trying to understand what observations they might be able to find that would help distinguish between rival hypotheses. And I'll come back to this a little bit later in one of my case studies. Okay, so that was just basically a kind of intro to some trace-based methods. I'll talk a little bit about the smoking gun stuff in particular in I think my second case study. But before we move on to looking at the case studies, I also just want to mention on the cosmological side of things, that we do have a kind of standard picture of the evolution of the universe. So on the very left-hand side, you see this afterglow light pattern. That's the CMB, really, that I showed you before. And then um, one kind of prominent uh, way of sort of explaining this whole history takes on a kind of narrative form, where you sort of have this kind of standard narrative that starts with some kind of quantum gravity era, a Big Bang, inflation, time of last scattering, all the way through over billions of years, the gradual formation of structure in the universe until we get to the present day, where we have sort of the galaxies and the galactic structure that we see. Um, I'm not going to emphasize this too much for the purpose of this talk, but I just wanted to flag that this seems like a nice case for making connections with um, the kind of role of narrative in historical explanations, because um, you know, this is a kind of way that cosmologists map out the history of the universe, pointing to um, contingencies, things, pivotal events that explain why the universe is the way that it is now. And so this is just another example of ways that there's these kind of parallels between the kinds of explanations that are given in cosmology as with other historical sciences. Okay, so just to summarize where we're at, um, talked about how astrophysics involves remote and inaccessible target systems. Um, there are no, for this reason, there tend to not be controlled interventions on the targets of study. Cosmology perhaps is even more extreme in this case, in that there really is a single object of study, the entire universe throughout its entire history. Um, and so intervening on, the whole universe and seeing what another universe would look like looks to be highly intractable, to put it mildly. For this reason, much of the evidence in astrophysics takes the form of traces, and so many of the kinds of methods that philosophers of historical sciences talk about in connection to other historical sciences are also going to play a prominent role in astrophysics and cosmology. So things like unification of traces by a common cause, search for smoking guns, consilience and coherence tests. Get to coherence tests in a second. And also the kind of role of narrative storytelling that we see, for example, in Lambda CDM and in one of my case studies coming up. So this is just kind of the general picture by which we might think that in some deeper way, astrophysics and cosmology have a lot in common with historical sciences. Their epistemologies are similar, and that they share common challenges and also common methods for dealing with those challenges. Okay. I'm going to get now into two main case studies. Um, Please feel free to interrupt me during these because, of course, they're a little uh, technical, and I'm going to try and just sort of breeze through them at a more abstract level. But if anything's confusing, please feel free to ask for clarification. Okay, so the first case study is the Hubble tension. So first of all, what is the Hubble constant? The Hubble tension involves measurement of the Hubble constant. This is usually designated H naught. And I put constant in scare quotes here because it's yeah, that's probably this kind of a misrepresentation of what's going on. But nonetheless, it's sort of commonly referred to as the Hubble constant. Basically, H naught gives the current rate at which the universe is expanding. And so the equation for this is V equals H naught D, where V is just the recessional velocity of something, caught in the sort of flow of cosmic expansion. And D is just the distance to that object. So if we want to measure H naught, we first need to measure the distance to the astronomical object. And specifically, it has to be an astronomical object that is sort of at least far enough away from us that we think that its motion is due to the expansion of the universe as opposed to sort of just sort of random motions or other kinds of motions due to its position in a galaxy or something. So first we have to measure the distance to an object. Second, we have to measure the speed at which it's receding away from us. Um, so uh, Sounds pretty simple. Unfortunately, it turns out to be rather complicated. Um, and in fact, the sort of best methods that we have for measuring the Hubble constant turn out to be in conflict in the sense that they um, have their best answers to date are not only sort of different, but different to the degree and with um, consideration of the error bars in question, uh, such that they're really incompatible. So the tension really refers to this 5 sigma over on the right here, um, which suggests that it's really not a matter of just statistics that they disagree, but really there must be something fundamentally going wrong, either with one method or both, if they're measuring the same thing and getting different answers. So this is something that's kind of emerged over time as the precision of the different measurements has increased. And so we can think of it as, in some sense, the precision of these measurements has, at least for one of them, must have kind of surpassed the accuracy of the measurement method to get this disagreement. So I should just say that the top, the blue measurements here are based on so-called early universe measurements. So they're basically based on the cosmic microwave background, which I mentioned earlier. And so they involve measurements of these kind of traces of the early universe. And then in order to get the current rate of expansion, H naught, they have to import some cosmological assumptions in the form of this lambda CDM model that was on a previous slide. So the kind of standard model of cosmology has been, it's been very successful. And so incorporating those assumptions doesn't necessarily seem controversial. Um, this is, perhaps maybe the first indication of those assumptions going astray. But I'm really going to be focusing on this second measurement, which is based on the cosmic distance ladder and based on really much later observations of the universe. And proceeds in a much more straightforward way where you're trying to figure out the distance to particular objects and then trying to figure out the speed at which they're receding away. The trouble is that measuring distances in astrophysics is hard. You can't just, put up a ruler and measure the distance to these objects. Things within the galaxy, sometimes you can use kind of more straightforward physical methods, bouncing lasers or what have you. But for the most part, when we're dealing with astrophysics, we have to be a little bit more creative. So what astronomers do in order to get measured distances to very far away objects is they use the cosmic distance ladder, which really involves a number of different methods, a number of methods that overlap in terms of what they can measure, that are then calibrated against each other. So we start off with some sort of anchors in the system, like parallax, which is really just a geometric method that only works for very close by objects. And then we use the overlap with the sort of next method in the system, a so-called standard candle. So standard candles work basically because they're objects with known luminosity. And so much like if you have a candle and you know how bright it is and you take it further away, you can measure how bright it is and therefore infer how far away it is. Same kind of idea is happening with some of these standard candle methods in astrophysics. If we can measure how bright they are, we know how far away they are because we understand how sort of intrinsically bright they should be. Essentially, the ladder then just proceeds with this kind of intercalibration at each rung along the way. The danger, of course, is that if there are systematic errors in any particular rung in the ladder, they'll continue to propagate through to for rungs that are further down or further up, I suppose, in this image. And so if we're trying to measure objects that are very far away, there's a lot of potential systematics that might be in play because all of the systematics from uh, earlier rungs are going to be involved. Okay, so moving on to think about what philosophers say about this case. Um, there have been a couple of recent papers that analyze the Hubble tension in terms of thinking about the value of agreement and disagreement across independent methods. So I'm roughly following the Matarese and McCoy paper here, although the Guégan paper talks about it in sort of fairly similar terms with slightly different language. I think there's kind of strong resonances between the two there. But roughly the kind of upshot of these papers, for my purposes, is first of all that there's that agreement that happens across what Matarese and McCoy call direct replication. So that's replication where you're essentially just trying to use the same method over again. So it should be at least nearly identical. If you have agreement across direct replication, then this is going to address the precision of the measurement. It's going to help you understand how precise the measurement is. It's dealing with kind of random errors. Second, if you have agreement across conceptual replication, so in their terminology, this means replication using highly independent methods. So we can think of um, the very old universe and very young universe measurements as being conceptual replication because they're extremely different. If you have agreement across those methods, then they address concerns of accuracy. They tell you you've got an accurate methods and accurate results via consilience. However, and what I want to focus on here, because we do in fact have disagreement, they also talk about the value of disagreement. And in particular, disagreement is most valuable when replication is across partially independent methods. Um, when you have small differences between methods, this provides a kind of easy tool for being able to isolate and identify plausible sources of unknown systematic error. So both of these papers emphasize different versions of distance ladders measurements as a potential avenue for identifying systematic errors in that distance ladder based method of measuring the Hubble constant. So the kind of main upshot here then is that disagreement across methods provides a guide for refining those methods. Um, and in particular, they're emphasizing this in the context of the distance ladder case. Now, what I want to do now is draw some parallels to a case in um, more Earth-based uh, historical sciences in order to emphasize really how similar the kinds of problems and philosophical upshots can be across these different contexts. So here I have just a version of uh, a presentation of the geological timescale or GTS. So, essentially this is doing something similar to what you're trying to establish with a distance ladder, and that it's creating a kind of system for measuring, how far back in time different things are. It's giving you a kind of time scale and also a kind of mapping of particular events to when they occurred in this time scale. So that's the kind of key idea. And so, I mean, really what I use this example as a parallel to the distance ladder because these are two sciences trying to do similar things in terms of getting a kind of systematic way of measuring distance or time when we don't have easy methods to just kind of directly measure these things. So, what do philosophers say about this case? So in particular, Elisa Bokolich has this nice paper from 2020 that talks about the GTS and describes some of the methods used in order to set up the GTS. And in a very similar manner, there's a kind of ladder of overlapping methods with intercalibration across the methods. So things like tree rings provide a kind of physical anchor, um, or sort of some kind of objective time scale. Uh, and this can then be cross-calibrated with radiocarbon dating. I guess I've written radio there twice. Apologies. Um, but the method is kind of similar in that you have these overlapping methods, and they're calibrated against each other in order to set up this time scale that stretches into the very distant past. Even though if you just sort of started with the last method in the rung, you wouldn't really be able to just measure it without having calibrated against earlier rungs. So one of the key questions that she asks in this paper is how should we understand the revision of the GTS? So there have been times where scientists have essentially come in and recalibrated and reset the timescale such that important events that were sort of previously dated at one time will now be dated at some other time. And so, you might see that and be very concerned. Um, but Bokulich instead wants to take a kind of more optimistic stance on this. And in particular, I'm going to focus on what she has to say about the role of coherence tests, which she thinks have been largely neglected by philosophers of science, at least relative to things like consilience, which we talk about a lot. So, Bokulich says that when we're in a position where coherence tests yield discordant results, so two different methods that overlap and are measuring the time to a single event. If they tell us different times for the same event, obviously that's a problem, discordant results. So what do scientists do in those situations? Well, they have four options. First, they can intercalibrate the methods. So if two methods disagree, you can just calibrate them against each other, solve the problem. Sometimes that might be the right answer. In other cases, they might independently calibrate one method and hope that it brings it into line with the second method. They might also change auxiliary hypotheses behind one method, so essentially changing something about the background assumptions that are going into the method, see if that fixes the problem. Or they might just do nothing. And the reason that they might do that is if they sort of come to this reach some kind of conceptual clarity where they realize that actually these methods shouldn't agree because they're really measuring different things. And so that can be a real source of insight too. So in this case, Bokulich argues that coherence tests offer a rich opportunity to identify errors and refine methods. And so we're reaching a very similar conclusion about what I take to be a very similar case between this case of astrophysics and the cosmic distance ladder and the case of the GTS and the geosciences. It's also worth mentioning that she places emphasis on kind of the iterative progress that happens in these situations, where you sort of gradually refine methods by identifying anomalies, trying to incorporate sort of more knowledge, take account of more effects, and sort of bring things into line, doing what George Smith calls closing the loop. And so instead of thinking of the revision of the GTS as something should be a source of skepticism, instead we should see this as part of the kind of iterative progress by which, especially something like a historical science, can kind of iteratively sort of become more precise and accurate through kind of identifying errors, refining methods, and doing all of these things kind of at once. Okay, so that was case study number one, drawing some parallels between the Hubble tension and the GTS. And really, I think that reflecting on that case study helps us, unlike the scientists who think of the Hubble tension as a real crisis and are very much in a panic over it, when we reflect upon the case of the the GTS and this kind of revision, I think it's much more natural to think of it in terms of this kind of iterative progress as a kind of normal part of how we refine our methods in the historical sciences. Okay, the next case I want to talk about is the case of black hole formation channels. So we now have lots of different observations of black holes for lots of different methods. We've observed supermassive black holes using the EHT to take pictures of some nearby black holes. Um, there are observations of our own galactic center, which also tell us that there should be a supermassive black hole there. We also have things like LIGO and that have been observing black hole binaries through gravitational waves. And now that we have all of these black hole observations, the natural question arises, well, how did all of these black holes form and evolve? Um, Black holes involve a lot of mass in a very small space, and it's kind of a puzzle to work out how that kind of thing could actually happen. So, um, there's various different populations of black holes, and they're thought to form in very different ways. So for the next few minutes, I'm going to talk about two of those populations and some of the struggles that scientists have had in trying to account for the populations of black holes that we observe in the sort of present universe. Okay, so the first case is the case of binary black hole mergers. So the LIGO-Virgo collaboration have now observed lots and lots and lots of gravitational wave signals originating from binary black hole mergers. And so we now have kind of a catalog of such mergers and some sense of the black holes that result from them. And so the challenge then is to infer the origin and evolution of those observed black hole populations. The basic strategy that gets employed here is to try and use a combination of um, simulations in order to infer some potential observational signatures of different formation channels. So do simulations of different potential processes and what the populations would look like if that process was dominant, um, and try and see whether, different processes lead to different black hole populations. Um, Essentially, whether there are distinct observational signatures that we might find in our observations of binary black hole mergers that would tell us what process was responsible for their formation. Okay. So here's just an example of some scientists dealing with this because I think it's a nice illustration. So this Son et al. Paper considers two contributing formation channels. One is called the common envelope channel. The other is called the stable Roche lobe overflow channel. Um, Basically, in case one, two black holes form within a kind of single envelope of matter from which they're gradually sucking in the matter to get bigger. And in the second case, we have this black hole uh, with, that's accreting matter from this second envelope around a giant star. And then eventually the giant star also becomes a black hole. But in one case, the two black holes are sort of together. In the second case, you have a black hole. And then the second one forms much later. So that's just kind of a very broad picture of these two proposed channels. The idea then is that the redshift evolution, which is to say, because redshift really is just a measure of how far away, or therefore how far back in time, an entity is in astrophysics. The idea then is that the properties of binary black hole mergers, as they're on sort of different time slices, looking further and further away into the universe, um, will sort of encode various properties about their formation. So what does this mean? On the first channel, the common envelope channel, you're going to favor low mass black holes being formed this way. Um, on the second channel, the stable RLOF channel, it's going to favor producing much larger mass black holes. There's this complication, and that there's also, they're not just favoring bigger or larger black holes, but they will um, produce black holes at different times over the history of the universe, because one process is just kind of faster than the other. So if we want to decode information about which channel is dominating based on current observations, we're going to have to factor this time delay feature in. So essentially, the first channel also favors short time delays, which means that it's going to dominate for objects that are sort of further back in time. If there's a short time delay, the black holes just form earlier. Versus the second channel favors long time delays, the black holes just form later. And so they're going to make a more substantial contribution at later times, times that are closer to us. And so there's this kind of complicating factor where they have this kind of signature in terms of the masses of the black holes they produce, but it's complicated by this other feature of exactly when we expect the black holes to form relative to us. So don't worry about the details too much here. The point is really that what scientists are doing is kind of grappling with all of these intricacies. They're trying to discover signatures of different kinds of channels of black hole evolution, different kinds of, um, and essentially looking for ways that they might be able to observationally distinguish between the contributions of these two channels. So, if we want to correct the binary black hole fossil record, so to speak, we're going to need to, do a lot of things to kind of correct for biases due to things like parameter estimation, biases from the time delay, various selection effects, accounting for parameter degeneracies. I'm not going to talk about, the specifics of those. But the point here is that much like what, again, I'm using Bokelich here, what people talk about in terms of correcting the black hole fossil record, it looks kind of similar to what needs to be done in sort of analyzing the contributions of these different channels. I'm not going to go into detail with the supermassive black hole channels here because I'm already talking for a little bit longer than I'd hoped. But a very similar kind of story can be told for supermassive black hole populations. We have these two different proposed channels for how these black holes could evolve. As with the binary black hole case, we have these two channels that are providing distinct how possibly explanations. Either of the two channels could provide a candidate explanation for the supermassive black holes that we see. In all of these cases, we can't observe the kind of original seeds of the black holes themselves. We can't observe the conditions under which they formed. We can't observe their sort of whole evolution. So instead, what we need is to figure out the signatures in current populations or of kind of later populations of black holes that would help us infer something about their evolution. There's this puzzle. Black holes seem to get a bit too big too early. I won't go into it too much, but that's the basic puzzle that needs to be solved. And here are just here's just a kind of visual representation of some of the proposals that have been put on the table. And then the challenge is to say, okay, given these two how possibly explanations, what properties of our observations might actually help us distinguish between the two? So it seems like in both of these cases, the binary black hole case and the supermassive black hole case, when we're trying to study the evolution of these objects, we need to get from a how possibly explanation to a how actually explanation. In doing so, what scientists seem to be doing is kind of telling a story, iteratively making it more precise, and trying to derive some observational consequences. And in the case of astrophysics, this is largely done via some kind of simulations rather. I think we can think of this in conversation with what Cleveland says about identifying and searching for smoking guns. The reality is that the kinds of signatures we're looking for, um, it would be nice to have some really pristine, clear smoking guns. The reality is that it's often a lot more complicated. Lots of different things have to be controlled for. Um, but the kind of ideal goal is to look for a really nice, clear observation that would distinguish between rival hypotheses, or at least tell us the relative contributions of these different hypotheses. Okay, so in the last few minutes, I'll just kind of try and bring some of these threads together and conclude. So we started off with this question, are cosmology and astrophysics historical sciences? Um, we said yes, I mean, in the very kind of relatively shallow sense that they deal with the distant past. Um, but also I think that the connection goes deeper. So they face some common epistemic challenges in the sense that they have these remote, inaccessible targets. In the case of cosmology, we also face similar kind of challenges in that we only have one history and we can't go back and intervene on the actual history to see how things could have been different. Um, in dealing with these challenges, I think astrophysics and cosmology employ some common methodological strategies with other historical sciences. So they employ various trace-based methods, such as the inference to a common cause, consilience, coherence testing, the search for smoking guns. And as we sort of saw briefly in the case of the lambda CDM and in the case of black hole formation channels, um, some use of narrative explanation as a way of trying to sort of uncover some of these smoking guns. Um, I've also said that I think that there are some strong parallels between cases in astrophysics and cosmology and cases in other historical sciences. So, in the case of the Hubble tension, there's a very strong parallel with the case of the geological timescale, and I think very similar lessons apply in these cases, which I think offers some hope for them kind of helping one another, both to be sort of more informative in our understanding of each of these particular sciences, but also hopefully in providing a kind of richer, more diverse base for thinking about historical sciences in general. One thing that sort of came through in parts, but I want to kind of say just a little bit more about before I conclude, is the idea of epistemic iteration. So this came up in discussion of George Smith's uh, theory of closing the loop, which Bokelich used in the context of the geological timescale. I think this also kind of connects to what Hasek Chang calls epistemic iteration. So he says this describes it as successive stages of knowledge, each building on the preceding one, are created in order to enhance the achievement of certain epistemic goals. So what this looks like in astrophysics, I think, is that there's this kind of iterative improvement in models, measurements, and the further exploring of dependency relationships, especially through simulations. There's a kind of bootstrapping that happens where you're sort of getting progress through a kind of self-improvement, um, even in the absence of a kind of secure epistemic foundation. There's these intertwined lines of inquiry. So, for example, we have inquiry into cosmology and inquiry into formation channels for black holes. These proceed simultaneously, and it turns out with a lot of mutual feedback. If you incorporate your cosmological model into some of these analyses, you can get more constraints and vice versa. And sort of by proceeding with these kind of parallel lines, doing things really at the same time, you're sort of gradually placing tighter constraints on the whole, which I think again has some kind of resonances with Chang's work in terms of his kind of coherentist epistemology. Okay, so final slide. Um, Hopefully through this, I've convinced you that there are these strong parallels between astrophysics and cosmology on the one hand, and other more traditional historical sciences on the other, and that there does seem to be this promise for fruitful cross-fertilization by bringing the philosophies of astronomy and cosmology on the one hand into conversation with philosophies of other historical sciences. I think we can learn a lot about learn a lot about historical science in general by incorporating a kind of more diverse um, collection of sciences that we are considering. And I also think that it'll be very helpful for learning about astrophysics and cosmology, to think of it as an historical science and bring all of the insights that historical philosophers of historical sciences have come to, bring those to bear on astrophysics and cosmology, I think can be very fruitful. Thank you.
Great. Thank you very much, Jamie. I think you gave us a prime example of this cross-fertilization, perhaps, already, by introducing the philosophy of cosmology to us, of which we usually don't talk so much. Okay, now it's the question and comment session. Who would like to go first? Is there any immediate question, concerns, comments, criticisms? Okay, I see Avi's hand. Maybe go first. Avi, please.
So, Jamie, really thank you very much for this paper. Number of virtues. First, really appreciate that you spoke on a level that even people who don't know much about cosmology can really follow the argument and understand what you're doing and the similarities with the philosophy of other historical sciences. The argument that cosmology is a historical science and the philosophy of cosmology bears a lot of resemblance to the philosophies of other historical sciences. You're preaching to the choir here. That's very much what, the assumption of the handbook for philosophy of the historical sciences. So again, wonderful. I hope that before long you'll come and visit us in Austria. But let me ask you then two questions. One, note that there was this kind of terminological shift in the, like, let's say two-thirds of the paper, because you started speaking about the influence of common causes, referring to Carol Cleland and so on. And then when you started talking about the black hole, you transitioned to talk about channels and information, which is an interesting thing because that's exactly what happened to me on a grander cosmic scale. That is, for the first, let's say, 15 years of this century, I was thinking about the historical sciences in terms of common causes. And then I started thinking, actually, this is not what's going on, because what we have is really common origins that transmit information. And let's start talking about common origins as sources of information, because not every cause transmits information. And sometimes information is transmitted without us knowing what is the causal mechanism that underlies it. So let's just, it supervenes on the causal level. So why don't we just talk about origins and information? That seems to be the shift you're making. The second question is, of course, as I said, you're preaching to the choir, but when I talk about philosophy of the historical sciences, I tend to say, well, there's a bit of an exception for cosmology for two reasons. One more minor, the other one is more major. The minor is that in cosmology, there are observations, as you just put it. And in all the other historical sciences, there are no observations. There are other ways of transmitting information. Obviously, this is not imagination and it's not arbitrary, but it's not in a visual sense. It's not observing the past, which is what cosmologists can do. The other thing, which is definitely distinguishes cosmology, I'm not sure about geology, is the relationship to what Larry Lawson called the pessimistic induction. Because here's the nice thing when you talk about philology, human history, Darwinian biology. There is every ground for an optimistic induction. Of course, we know much more about biology today than what Darwin knew. We know much more about history than Ranke did. We know much more about philology than the founders of philology in the 18th century did. Many more languages. But we haven't really there was no overhaul. There was no paradigm shift. There was no scientific revolution. What Darwin thought is, in every major way, is what we think. What Ranke knew about history, we accept. We don't say that Ranke was wrong. So he had his limitations, but it was not overhauled. Whereas in cosmology, the evolution resembles much more the evolution of physics because it's so close to physics. We have revolutions and things that cosmologists thought for a good reason in the previous century or in the 19th century. We just know, I mean, the universe is not stable. The universe is not eternal. We used to think for good reason that it was. And now, of course, you talked about the Hubble tension, because we used to think that there wasn't any, then we started believing that there is, and now we think that it keeps changing. It's not a constant, really. Here there is the ground for pessimistic induction, unlike in other historical sciences, I always give this example because philosophy of the historical sciences is treated like the bastards of philosophy of science, illegitimate. And I say, hey, actually, we have a much stronger ground for calling ourselves a science, because once there was one scientific revolution at the beginning, we just stick with it. Nothing. We have much stronger case to say that we have knowledge of at least the human past and the biological past than you physicists have that you understand the universe. Okay, I'll stop here. Thank you.
Great. Lots of really interesting things in there. So thank you. Thanks so much for all those comments. Yeah, so to start, I guess with the second point about the pessimistic meta-induction. That's really interesting. I don't know enough about the other cases to say much about the kind of optimistic induction side of things. I just don't know enough about the details of those sciences. I don't know how I feel about thinking about the contrast between an optimistic and a pessimistic induction as a kind of reliable, a kind of guide to the reliability of the knowledge that we have in those fields. But it's certainly an interesting point, and I always do like the kind of subversion of the kind of common narrative of physics is supreme, despite being a philosopher of the physical sciences. So I like that argument is being made, even if I don't know if I completely agree with it. Now to go back to this point about the terminological shift that happens. I think it might be giving me a little bit too much credit to say that it was a kind of deep conscious shift in the way that I was thinking about these things. I think I probably just made that terminological shift in part because I was making the shift between talking about what people say in the context of historical sciences and then kind of, I guess, using the actor categories of the scientists themselves when they're talking about these things. I hadn't really reflected on the fact that the use of the term channels indicates thinking about information channels. And I kind of wonder whether there's anything to that kind of metaphor in the way that the physicists themselves are talking. Because, what they're describing really is, what they take to be a kind of causal evolution. They think, there were the very early universe, there were these black hole seeds that accreted matter onto them, that either you need really big early seeds or you can't get black holes as big as we observe now. Or if you have small seeds, you need some really, really finely tuned ideal conditions for black hole growth. And then you sort of progress that story the whole way through. But it is kind of telling to be thinking about the kind of signatures and the kind of information that we have at the end of this. And I don't really have anything kind of deep and interesting to say about that goes beyond this, but I think it would be really interesting to explore whether there's kind of something more going on in guiding how the scientists are thinking. If they're using language that sounds like information channels, like is that the kind of paradigm that they have in the back of their minds as they're thinking through these methods? I don't really have an answer for that, but I think it's really worth exploring.
Because that's your field and not mine. You think about black holes, about singularities. Black holes and singularities can have causes. They can't have origins because there's no information can't pass through singularity. There's a distinction. And the information, but they can send information. But the information is not from what was before the singularity. If when we talk about the Big Bang, the word before makes any sense at all, of course, maybe or not.
Okay, we have two more in the meanwhile. I mean, we can come back to that later if there's time. Next is Luis Saidan Duarte. I hope I'm not butchering that name too much. And then it's David.
Hello. Are you listening to me well?
Mhm.
Okay. So for those of you who don't know me, I'm Louis. I'm getting my PhD in the University of Brasília in Brazil, in history of science. And congratulations, Jamie. Your talk was just amazing, so insightful, so provoking. My question is just one, but it's a little complex, so I wrote it down. I hope you don't mind that I read it.
Yep.
I do see what you mean when you say that cosmologists and astrophysicists look for traces, like the cosmic wave background and the redshift in the light coming from distant galaxies, to reconstruct the story of the whole universe or some parts of it. But I think the great difference here is that while history, geology, paleontology, and evolutionary biology piece together their stories directly from the evidence of the past, cosmology and astrophysics base themselves primordially upon physical theories, such as general relativity and the Big Bang, which are made up of mathematical models and some underlying philosophical assumptions. For instance, it is only based on a mathematical model, namely Friedman's derivation of Einstein's general relativity equations, which is itself based on the cosmological principle that assumes that the universe is homogeneous and isotopic in larger scales, that we get the story of the Big Bang, uh, like rewarding the tape backwards in time. The way astrophysicists treat the historical traces that they experimentally collect is mostly as an evidence to support or refute these previously constructed mathematical theories. So in this way, I feel like they still impose a logical mathematical framework that biases how the historical evidence is read and understood. So in a few words, I think that the math still comes first here, and the historical evidence actually comes rather second as an index for judging which mathematical theories are better or worse. So I would just like to hear your thoughts on that, because I feel like, just like Professor Tucker said, there are some fundamental differences in the way that these two scientific fields evolve. So just want to hear your thoughts on that.
Yeah, so this is a really interesting question. I mean, I think the first thing to say is that I mean, I can agree with you that the mathematical and the physical theories are obviously playing a really strong role in the in cosmology and astrophysics, to an extent that, arguably goes beyond what's going on in um, other other cases of historical science. I mean, the theory in this case is, preceded observations. Um, in many ways, it became, the theory is much more developed in a lot of cases than and kind of more well worked out and reliable in a lot of physics than, necessarily the observations are kind of struggling to keep up. Um, that said, I mean, I think a lot of the recent progress in cosmology has really come on the back of the observations. And I guess also to kind of loop back to a point that I think I didn't quite address with an Avi's questions. The observations are super complicated, and the way that astrophysicists talk about them being as observations, I think really misrepresents what's going on in many ways, because there's a really strong reliance on theory and models in the process of the observations in ways that are really complicated, which, you know, involve kind of heavy theory ladenness of the observations that has to be dealt with. And they're they're very strongly intertwined in the kind of astrophysical observations. Um, Now, does this make them all that? Did I guess I'm the heart of your question seems to be, does this dynamic where there is this kind of really strong dependence on the sort of physics and the math, does this make them kind of distinct from other historical sciences? And I'm more of an expert in the astrophysics side of things than I am in the other sciences. So, in part, this is going to be an answer from a little bit of ignorance. But at least my impression is that although the nature of the theories, so what say Curie calls mid-range theories that make these connections between the traces that we have and the systems that we're interested in learning about, these are going to be really diverse across different sciences. But I think that they're always playing an important role. Um, you know, if we want to take the fossil record as indicating anything about the way that the past is, we need to say a lot about how fossils form and the conditions under which they form. We need to be correcting for all the kinds of biases that get introduced in the process of fossil formation. Um, and there's also a lot of theory that goes on at the level of our models of, say, organisms and the relations between different kinds of morphologies of organisms, and how we kind of can infer from, a single, fragment of a skeleton to what the organism must have been like. I mean, you're building that on a lot of theories based on it's the analog of our physical theories in this case would be various kinds of biological theories we have about, say, mammals, and the kind of relationships between their I think this is another example from Curie's book, so I'm just being a big fan now, I guess. But I think there's the example of the tooth of the platypus and how much you can infer from about the entire you know the entire species based on that one little fragment. And to me, that sounds very much like what's going on in physics and astrophysics. So what initially looks like a difference, I wonder whether there's actually it actually is more parallel. It's just that the theories themselves are quite different.
If I could just jump in, Arthur Danto said nobody walks naked into the archive. And what he meant is that we always come with a theory. A theory can be very sophisticated, highly mathematical, but even Ranke's basic insight was memories are not reliable. So you can't trust memoirs that were written 30 years after the fact. We want to look at diary entries that were written in real time, diplomatic reports were written in real time. Now, that's not anything as sophisticated as what cosmology does, but the theory is there. And that's because of the lack of observation. If you can't observe, there's no given. Even in history, when you think, Napoleon, or George Washington, everybody, I know 100% there was a George Washington. Still, nobody has observed no historian has ever observed or will observe Napoleon. There has to be some theory about the archives, about what is preserved and how to deal with it. So the theory is always there. It's just different theories. And of course, my opinion is these are all information theories, but that's a different story. David.
I
Next.
think we are pretty much on the same page, all of us. And I just think that like the mathematical background that physicists often rely so much on often allows them to create stories that are so wild and difficult to abstract from the philosophical principles that they were based on. So when we are dealing with historical sciences like biology, which have to be more attained to the fossil record. I feel like the stories, the narratives that we get, like the selection is just so stories. They have to explain the evidence in the end, and not the other way around, and not the evidence proving that the theory is correct. So I feel like this changes a lot the stuffs. But I do think that this way of seeing things is very fruitful, this cross fertilization, and yet there's a lot to come.
Okay, I think next is David, and then perhaps me if there's nobody else before. But let's see. David.
Okay, thank you very much for the talk. I enjoyed very much, and I also enjoyed the discussion so far. A lot of good points on every side. I would perhaps like to expand the scope a little bit further, because Carol Cleland, Derek Turner, Adrian Curry are often discussing some other types of methods with regard to historical sciences, which I think haven't been discussed so far, like experimental methods. How can astrophysics, astronomy benefit from the experimental method? Or, for example, another topic I'm a little bit interested right now is inference from absence, when you can inform some information from the absence of a trace. Can you think of some good examples of useful experiments in astrophysics, or would it be tied mostly to calibration, for example? Thank you.
Great. So yeah, there's been some recent work, especially by Nora Boyd, on thinking about the role of kind of ordinary experiments in astrophysics. And so in particular, some of the cases that she looks at are cases where astrophysicists claim to be doing astrophysical experiments, by sort of intervening on maybe some like high energy, I don't know. I can't remember the details, but essentially they're looking at the similar kinds of materials, that they think are, occurring in these distant astrophysical systems. And so they're thinking of it in the sense that if you think of this kind of broader target, which might be physical systems that are kind of characterized by this particular equation, or exhibiting these kinds of phenomena. And if there happens to be an instance in a lab and an instance in space, then it's kind of classic astrophysics. Then by doing an experiment in the lab, you're really doing an experiment on the same kind of thing, the same kind of system as you see in space. So that's kind of an example of ways that astronomers can do experiments. You might think of there being something kind of similar. There's similar kinds of things that you can do in other historical sciences. So if you are interested in, mammals, you can, look at mammals that are currently existing, look at a, particular taxa, and use those kinds of experiments to draw, more general conclusions that also apply to an extinct species. That it's just exactly the same kind of analog reasoning, I think, that's going on there. Or not even analog reasoning, in the sense that you're really kind of just choosing a broader target group in the first place. So that was the specifically the experimental side of things. The point about the inferring from absence, I'm trying to think of an example, but it seems to me like the kind of thing that must be going on in astrophysics all the time, whether or not it's actually kind of clearly stated, because so much of the time. So here's an example that might be a case of this. So recently, or somewhat recently, LIGO detected gravitational waves from a binary neutron star merger. And what's exciting about that is that if they're neutron stars rather than black holes, then when they collide, it's not just dark, they also produce basically a big explosion known as a kilonova. But these had never been observed before. And so in order to actually draw the conclusion that the gravitational waves were produced by a binary neutron star merger that was associated with this kilonova, basically to kind of prove the kind of association between these things, one part of the argument was thinking about the background rates of observed transient events. So something like a supernova is a transient event, and that it produces a really bright point in the sky that then only lasts for, an order of like weeks or months or something. Um, and so there are these long-standing surveys that astronomers have done where you're just sort of looking at the sky over long periods of time and just sort of counting the number of these transient events that occur. And over the course of this period of time, um, you know, very low, you have a kind of established rate of these events, and no kilonova events. Nothing matching our models of kilonova events occurred. And so from this absence, you can infer something about the rates at which these events happen. That then becomes important for making the association between the observed gravitational waves and the observed transient that they found afterwards. Because if these kilonova events were happening all the time, then the kind of coincidence of these two signals at the same time wouldn't be very good evidence that they were actually coming from the same event. Um, and so, if in order to make that kind of argument from coincidence, you do need to say something about how often, what the backgrounds
Mm.
of these kinds of events. And so
Yeah.
it seems like the absence of evidence of these events previously is really important
Mhm.
for making the argument from coincidence.
Yes, and that's a very good example also to show that in order to infer something from the absence, you need a very theory-loaded background. So,
Yeah.
okay, yeah.
Okay, great. I don't see any immediate hand, so I would put myself in, even though my primary role here is to be as moderator. But I would have a question similar to the whole discussion so far, perhaps. Maybe this is a question that's a bit premature, and maybe it's for all of us, but I would like the general question is, and let me explain what I mean by that. To what extent do you think cosmology is a prototypical historical science? Of course, by then we would have to know what a prototypical historical science is. But we at least have some models right now. I mean, Avi gave us some examples what might differentiate it. It's empirical, and maybe what he calls the optimist induction doesn't work. And then you gave us examples of or how it is a historical science. Ontologically, it's about tokens, or even just one thing. There's only one of them that might differentiate it too. Then epistemically, it's about, of course, traces and the unification, and it's also narrative informed. It can be often very narrative informed, which is together with the other historical sciences. Now, but if you think about the historical sciences proposal, I think we got two or maybe three basic understandings of what historical sciences are. One is Carol Cleland and her traces and the smoking gun. Do you think that I mean, it's very hard to answer. There will be a smoking gun, or the smoking gun analysis is applicable to cosmology? I mean, it's probably very hard to explain. And the other is sort of what Adrian says, sort of that historical sciences and Cleveland is too trace centric. Historical sciences are much more complicated, do all kinds of this theoretical omnivore stuff. And Adrian actually says that historical science have less in common than with each other than with some experimental science. So and in some sense, he throws down the whole proposal, but let's not talk about that. So do you think it then leads more to that side? And then maybe a little follow-up question by that, what does it exactly mean that cosmology wants to explain the whole of the universe, or the universe as a whole? So or this understanding that is sort of there's only one token, which I mean, the historical sciences usually there are quite a few tokens around of which you want to explain, but there's only one. Does that also make the cosmology in a very specific sense a, um, a historical science? I'm not sure about this ontological point, what it actually means for something to be. There's only one of them, and it's the universe as a whole. What it means to explain it as a whole. What that would exactly mean. I mean, there's some good logical reasons sometimes that you cannot explain the whole as a whole, but maybe that is not the case for cosmology. I'm not sure, but I think that would be. Maybe these are two questions, perhaps more. I'm not sure, but thanks.
Great. So those are some very big questions that I absolutely can't give you
Sorry.
real answer to, but uh, very, very interesting questions. So with the first question about, to what extent is cosmology a sort of typical or prototypical historical science? And I think you're right that that is going to depend pretty heavily on what you take historical science to be. Um, Certainly in my contribution to the volume, I kind of just try and sidestep that issue because um, I don't personally feel like I have a good sort of grasp on what the right answer to that question should be. Um, I think that we can, I do think though that we can get a lot out of drawing comparisons between different historical sciences, um, without necessarily having to have a good answer to that question or having to, take a strong stand on, whether ultimately historical sciences are this kind of like clearly delineated thing that are going to be, whether there's going to be some nice demarcation criteria we can give, or whether actually in the end historical sciences are really just have as much in common with other sciences as they do with each other. I don't think we have to answer that question in order to, um, find the ways in which they do have similarities and draw some conclusions and hopefully get this kind of cross-fertilization going. Um, and yeah, in terms of choosing between the different pictures you describe, I'm not sure that I even want to try. But with the second question, what does it even mean that cosmology is trying to explain the entire universe, so to speak? Um, I think that, stated as it often is stated, cosmology is clearly overstating what it's capable of doing. Um, and in terms of what it's actually aiming at, I think really what's going on is cosmology is trying to explain the origins and evolution of the universe on very large scales. So it's trying to get the really big picture right. And once you transition into getting kind of the details, that's really transitioning into what astrophysics is interested in. And so when cosmologists claim to be sort of making things work, it's because their simulations, starting off with kind of throwing in the right kind of stuff in the early universe and progressing through billions of years in order until you sort of get formation of galaxies and galaxy clusters and this kind of characteristic web of kind of galaxies and these threads and then these big open voids in between. Um, if you can get that picture right in a kind of statistical sense, such that your observations of the nearby universe, statistically in terms of like you know, the distribution of stuff, match on to what your simulation says, then I think that's what you're looking for. That's kind of a success. Now, it gets more complicated because there's feedback between the kind of specific astrophysical processes that are important to the large scales. So black holes are thought to be important. There's kind of strong correlations between the supermassive black holes in the center of galaxies and the properties of the galaxy, which suggests some kind of feedback between the two that isn't yet super well understood, as far as I know. And so there's a lot of different processes on the kind of smaller scale, like the rates of supernovas and things, that become important for cosmology to get the right stuff, even on large scales. So it's not a kind of clean delineation between the two. Um, but I think it's also clear that cosmology isn't trying to sort of say exactly where, Earth is going to form, based on some kind of initial data. It's never going to get that level of detail right. And so, um, I think other sciences are pretty safe from some kind of attempted reduction to cosmology.
Okay, great. Thank you very much. That was very helpful and very broad in your answer. Thank you. Is there, I see no hands at the moment. Is there anybody else? We would have a bit of time. Jamie had been doing very well so far. It was probably also exhaustive, but there's a bit more time if maybe one or two more questions at most, if there's something. Of course, we don't need to. Well, if not, we already at 1.5 hours in, which is great. Then I say thank you very much to all of you again, and especially thank you very much for Jamie for her talk, and of course also for these knowledgeable answers to our questions. And we'll see each other again on the 29th of May with Arthur Faisassi speaking about Koselik and his concept of history. Thank you very much. See you next time.